In this presentation, we're going to look at two applications, Newton's law of cooling and logistic growth. Both of them are based on first-order differential equations. We're going to explore both of these examples in terms of the theory of equilibrium points and stability that is discussed in the text, and discuss how the predictions that are made by that theory relate to what happens with the analytical solution. So first of all, we're going to look at Newton's law of cooling, which is discussed in the book on page 20. There's your differential equation. It's a first order ordinary differential equation. It's linear. Small t stands for the elapsed time in some process where some object is warming up or cooling off. Big T as a function of little t represents the temperature of the object that's warming or cooling. T sub m represents the temperature of the medium, which is assumed to be constant. The medium typically is something like a refrigerator or stove, or it could even be something that's left in a room and warming up or cooling down to room temperature. K is a positive proportionality constant. Now if we carry out the stability analysis on the differential equation, notice that there's only one equilibrium solution, which is, by looking at the right-hand side, there's only one solution that makes the right-hand side of the differential equation equal to 0, and that's the value t equals t sub m. So that's our only equilibrium solution, and now we investigate that equilibrium solution when t is greater than t sub m, keeping in mind the fact that k is a positive constant. Looking back at the right-hand side of our differential equation, when t is greater than t sub m, the expression on the right-hand side is going to have a negative value, which is going to cause our temperature to decrease. And similarly, if t is less than t sub m, looking back at the differential equation, the expression on the right-hand side will be positive, which will cause the temperature to increase. So that means that that value is a stable equilibrium. Physically, that tells us, as we would expect, that the object cools off if it starts out hotter, and it warms up if it starts out cooler. There's a sketch in this presentation and a better sketch in the text. The exact solution of Newton's law of cooling is left as a homework assignment, and you should be able to show, using, since it is a separable differential equation, using those techniques, you should be able to show that that equation on the bottom of page 1 of this presentation is indeed the exact solution. For our next example, we're going to look at logistic growth, which is discussed on page 21 in the book. And here's our differential equation. Again, it's a first order differential equation, but now the right-hand side function is nonlinear. We have two equilibrium points, one at n equals 0 and one at n equals k. In this differential equation, t represents the elapsed time. N of t represents typically the number of people in a population. K is a positive constant called the carrying capacity. In a typical application to population studies, K represents the fact that a typical environment only contains so much food and other natural resources, and as the population increases, eventually the typical population is going to level off because of limited resources. And that's what we will indeed end up seeing in our solution. So small t is the elapsed time, n of t is the total number in our population, k is a carrying capacity, which is assumed to be a positive constant, and r is a positive proportionality constant. So we're making a lot of assumptions here, and those assumptions may or may not be valid. That's the job of a biologist to tell us if those assumptions are accurate or not. But based on those assumptions, we go ahead and analyze this differential equation for the stability and see what that tells us about the solution. So if we start out with our population larger than the carrying capacity, again looking at the right hand side of our differential equation, keeping in mind that k and r are both positive constants, that's going to cause the right hand side of our differential equation, that expression, to be negative, so n is going to decrease in that case. In a typical application, n starts out between 0 and the carrying capacity, and then that expression on the right hand side is positive, and the population increases up to a point. But notice in the differential equation and in our graph, as n approaches the value of the carrying capacity, that difference becomes smaller and smaller, and the effect that has on our differential equation is our slope starts to become smaller and smaller, so the graph starts to level off. This is not very realistic, but if we somehow started with n less than 0, we would get the derivative to be less than 0. So n equals 0 is an unstable equilibrium, n equals k is a stable equilibrium for this problem. So if the population starts out larger than the carrying capacity, the population will decline and approach the carrying capacity. In a more typical application, assuming all the assumptions we're making about this model, if the population starts out between 0 and the carrying capacity, it'll start growing exponentially, but then the concavity will change and it will still increase, but it will increase slower and slower as it approaches the carrying capacity. The exact analytical solution was left as a homework problem. You should get that. There's quite a few hints in the solution. So if you need help with that, it is a little bit complicated derivation, but it's similar to some of the other problems. So if you need help, let us know.